And so I'm going to be talking about giving an introduction to time series in the form of Fourier analysis. So I think probably most people have seen Fourier analysis in your undergraduate degree programs, maybe even in a graduate course. And so I kind of struggled to figure out quite how to position this talk in a way that introduces the subject, but also respects that a lot of us are probably at least think of ourselves as at least being very familiar with it. So I hope I haven't gone too far in the other direction. I tried to make it interesting and entertaining. The other part of this is that it's a subject that is very field specific. So every field that does Fourier analysis, which is everything from like electrical engineering, numerical fluid dynamics to astronomy, we all have our own separate jargons, our own separate conventions, this sort of thing. I tried to be as agnostic to that as possible and also highlight it. But certainly as a graduate student, when I was doing this kind of thing, and I would misspeak and people would call me out on it. So I guess what I'm trying to say is it's okay to not have perfect command of the jargon of Fourier analysis. Hopefully it'll be a little bit better today. And hopefully my talk will be clarifying and not muddying the waters. So our goals for the lecture today are to, and I sort of wrote this as a kind of also an introductory talk. So understanding what time series are and what the generalizations of time series are and how they show up in different areas of astronomy. As Adam said, the primary goal, perhaps the primary goal of LSST is to measure the time varying sky. As I sort of just alluded to, also a lot of the same underlying approaches for understanding the time varying sky apply to our ability to understand problems in sort of static sky astronomy or cosmology and astrophysics. And then, as we'll learn about on Thursday, careful analysis of time series have also revealed an entirely new window into the universe, which is gravitational wave observations. So time series methods are almost all sort of developed out of Fourier analysis and have historical roots. So even if a method isn't directly Fourier analysis, you're going to see presentations that will leverage intuition from Fourier analysis to some new method that may have very different conceptual underpinnings. So we're going to start with Fourier analysis. The first lecture is to understand how to construct Fourier series, which is a sort of discrete version. Confusingly, there's also a discrete Fourier transform. We'll talk about that. I think we're going to skip over it a little bit in today, but at the next session, I'm going to focus more time on it because it brings up some interesting kind of software engineering things about how you write fast algorithms for performing Fourier transforms. And then we'll move to the continuum limit from the discrete limit and generalized to non-repeating signals, and also generalizations, general stochastic processes, so not just something that's varying. As always, I like to tell you what my pedagogical framework is. So as I mentioned, this is a really old field, and I'm going to try and cover about a semester-long, maybe first-year graduate level course in reduction in a total time limit of 90 minutes plus 90 minutes of problems. So apologies in advance. Yeah, as I said, sort of focusing on methods and jargons, and then trusting you that you'll get the cultural specifics from your subdiscipline when you need it. I'm going to give this sort of a rough overview. As I've kind of said, we're going to start with the discrete case, move to the continuum case, and then add computations, and then I'll talk about some modern extensions of Fourier analysis in the afternoon. I also like to always give some good references. So the one that these notes are going to be based on is really this Fourier transform and its applications by Cosgrove. This is an extension of a very old set of lecture notes that's been given apparently at Stanford to electrical engineers for like 40 or 50 years. And it's how I learned this stuff originally, and it's how most people, I think, originally learned it. These were a very classic set of lecture notes. If you have any questions about any of the material, it's in here, and it's going to be presented really well and really compelling. Also, our kind of standard reference for everything in DSFP is the statistics, data mining, machine learning, and astronomy. And these are all LSST people, so everything in there is specifically geared towards LSST science. And then a book that I like, which I'm going to be honest, is very out of date and not the best learning material, but it helped me to sort of get a lot of the basics and think about interesting problems, is the statistical physics of cosmic structures. And there's, in particular, there's a really interesting discussion that I'll touch on in this lecture about using measurements of clustering, Fourier transforms of clustering, to constrain the fractal dimension of the universe, which is a thing that people cared about, and it turns out the universe isn't a fractal, so nobody cares about it anymore. But it's fun to think about. So that's a really nice research grade. Okay. So a very natural place to start the discussion is by asking what are time series methods for? And the answer is representing periodic signals. So if I give you this plot, which might be a little bit small, hopefully everybody can see it, how many frequencies or how many periods are present in this signal? One. Yeah, super complicated, I know. What about this one? Any guesses? You're saying one also. I feel like there might be more than one, but not a lot. Yeah, I think it's, I have to go back and look, but I think it's. All right, what about this thing? Any guesses how many frequencies are present here? 10's a goodish answer. So there are actually 32 frequencies present. So, what are some things we'd like to do with signals of this type? Well, we'd like to do two things. One, we'd like to characterize correlations. So, are there correlations in time or frequency in my periodic signals? And I guess by definition, a periodic signal is going to have at least a correlation at the period of the signal, right? And we'd also like to be able to predict, or in the time series jargon, we'd like to forecast future values, right? So in astronomy, we see a lot of characterizing correlations. If you were an economist or a finance person, you would be doing a lot of predicting what time series are going to do. So yeah, so as I just said, in astronomy, we focus exclusively on characterizing correlations. We will see a little bit about forecasting later in the week. We'll just briefly touch on it in Sharon's talks. As an example of a forecasting task that I've actually worked on and I have some published papers on is forecasting the rotation state of one of Jupiter's moons from orbit perturbations to try to measure the ice shell thickness and whether Jupiter's moons have liquid water pressures. So yeah, so I sort of said this already, but really just trying to give you a kind of brief introduction and respecting the fact that you have some domain knowledge already. Okay, so a definition of what even is a periodic time series. So we're going to look at signals in this form. So we'll have some time series signal that's W of t in this case. And W of t could be the output of some dynamical system we can call L, and it's acting on maybe something else that's varying in time, right? So there's some complexity. We can characterize our signal W of t and learn something about L, or we can try to learn something about some other signal that's embedded in our system. If a signal has this form where W of t plus some fixed constant period t is equal to W of t, then we call it a periodic signal. So different applications are going to ask us to put some requirements on the nature of this W of t, which is our time series itself, or maybe some requirements on the system that is processing our inputs V of t. And a couple of the requirements that we try and put on are, sort of linearity and homogeneity, right? So what we want is the system acting on our space inputs to equal our system, the sum of the system acting on the individual inputs. And we also want to be able to pull out sort of information, right? So it turns out that these requirements are enough. These are so-called the principle of superposition, which we're familiar with. And these requirements are enough to be able to do a lot of time series analysis with a lot of Fourier analysis. So some possibly non-trivial observations that we're going to use to sort of do this analysis. So one really nice thing is that sine and cosine are periodic functions. And we know what sine and cosine look like. So if we're going to model a periodic signal, it would be nice maybe to write our model for periodic signals in terms of sines and cosines. Maybe a little bit less obvious is that this statement is true. If I take the magnitude of this integral, it's less than the magnitude of this integral, which is less than infinity. And functions that have this property are called L1 integrable. And it turns out that L1 integrability is enough to guarantee that all the Fourier analysis that we want to do will work for all functions that obey this, but there are actually functions that have well-posed Fourier transforms that are not in L1. So we're actually going to need some other requirements to generalize to the space of functions that we care about that doesn't actually obey this condition. Another possibly non-trivial observation that's going to help us here is that the complex exponentials, if we take products of them, they're orthogonal, right? So that means that we can expand things in the basis of complex exponentials. And you can sort of motivate why you would care about that for the fact that this expression is trivial, right? So statement 3 and statement 2 are related, and that's why the Fourier transform or Fourier analysis works. Is because the function follows this, then we can take products of these exponentials and generate Fourier transforms. So I sort of said this, but the relevance, yes.
Sorry.
Oh. Yeah, go ahead, sorry.
The statement you were saying that any function f of t that satisfies criteria can be used.
Yeah.
But not all functions f of t.
There are functions that you can that have a well-posed Fourier transform that are not in L1. But if a function is in L1, it has a well-posed Fourier transform, right? It turns out that, yeah, we'll get to the full criteria for other functions that have the perform Fourier transforms that are not in L1. What was your question? Or did you have a question? Christine?
Could you remind us to explain qualitatively this condition one more time?
Yeah. I'm not sure that I have a good qualitative explanation. Yeah. It turns out that when you work out the mathematics of this, that when you perform this integral, this is a Fourier transform integral, we'll see in a minute. When you perform this integral, it has to be finite, right? Yeah, I don't have good intuition for this, but it is a mathematical condition on when the Fourier transform exists. But
so the function of t will be the expression of the Fourier expression of sine t of cosine t, right?
So this is just your function, and we haven't performed the transform yet. So if we compute this integral, and if it's less than the magnitude of f of t, then we will be able to generate this well a finite value instead of a finite value. Yeah.
So is it independent of what can we find it exists? Are those two things?
I think in this case, yes, but I'm not a mathematician, right? So I'm sure somebody will have a counterexample, right? But in this case, this is the condition for being able to compute this integral. This integral is the Fourier. And again, I'm going to give you a bunch of other conditions. In practice, as astronomers, we never worry about this, right? Okay, so to summarize this, all of it, what this is saying is that we want to find an operation, which we're going to call the Fourier transform or the Fourier series, which takes an input signal in the time domain and converts it into a series of sines and cosines. And when we say it converts it into a series of sines and cosines, because we have these integrals that look like this thing looks like a least squares expression. So when we say a sum of sines and cosines approximates a periodic signal, we're saying that it approximates it in a least squares sense. And how we're going to do this in practice is with complex exponential representations of sine and cosine series. And so our integrals are going to have complex exponentials rather than sines and cosines in them. But taken together, we have a way to approximate periodic signals in a way that also gives us sines and cosine series, which we know how to interpret. That's the big idea. This does not seem to be rendering correctly. I will fix this when I post this, but this is going to turn out to be our Fourier series representations. So for functions that have a Fourier series, which is for a periodic signal and a discrete representation, we can write that function, this should be f of t, as a series of a sine functions plus bn cosine functions. And the coefficients a and bn are going to be given by these integrals. So those are just the definitions, and all this is I'm just projecting my signal f of t onto my sine basis and my cosine basis.
What's the expression of A naught?
A naught is pulled out as a special value that sits out in front. It turns out to be the average value of the function. And you can see that because this guy has a sine of 0. So you just get the t, average value. By the mean value here, calculus 1, that's the average value. Sometimes, as a bit of jargon, sometimes this is called the DC term in the Fourier series. So you'll see that in the problem set. Okay. So how does this work? And I again apologize, some of these figures are a little small. I tried to make them bigger and I couldn't get it corrected properly. So this is a triangle wave. So it's just a triangle repeating. And to prove that this actually works, I have plotted the Fourier series for increasing numbers of terms. So I have n equals 1, n equals 3, n equals 5, all the way through n equals 101. And I start to get the sum of sines and cosines that starts to approximate a triangle wave. If you'll notice, it does a really good job along the sort of sides of the triangle, but at the corners, it doesn't do a very good job. And one of the problems we'll ask you to explore why it fails there. Yeah.
Is there a reason why n odd?
What was that?
Is there a reason why n is odd?
Is there a reason why n is a lot?
Odd?
Odd. No. Just numbers like that. Okay, so that was for a signal that is strictly periodic, and now we want to move to signals that are not periodic, like we tend to encounter in astronomy. So how are we going to do that? So we're basically going to say that a non-periodic signal is secretly a periodic signal. It's just that the period is infinitely far away. And so something I learned in preparing these lectures that probably all of you knew is that the word analysis means the study of a limit. So when we talk about Fourier analysis, we're introducing a new kind of limiting process, a new notion of limit. And so that new limit is essentially this limit as t goes to infinity. So I'll ask you to sort of explore that for the rectangle function in the problem set. But I'll go ahead and give you the results or the answers to that problem. So I'm plotting just a few Fourier terms. So this is a discrete Fourier series representation. I'm just plotting the first few terms. And what I've done here is I've plotted a function that sort of bounds the first few terms. And then I've added some more terms. And then I've added some even more terms. And we start to get this really nice limiting function. So as we add more terms in our Fourier series, as we go to longer and longer, basically terms that are capturing periods that are larger and larger, we start to derive this limiting function. So what is the Fourier transform? The Fourier transform is the operation that gives us this bounding function for an infinite number of series covering periods going to infinite length. And this function is super famous in electrical engineering. You see it, I guess, I found all these pictures online of this like carved into the side of electrical engineering and engineering buildings and stuff. So this is the Fourier transform of the rectangle function rather than the triangle function. So as I just said this in words. So yeah, so can we derive an operation that gives us that limiting function? The answer is yes. We wouldn't ask the question if we couldn't, and that function is called the Fourier transform of f of t. Something that I also didn't really appreciate as a graduate student, but the domain on which the Fourier transform is defined is a vector space of functions, not actually the time domain or the frequency domain, right? So we often talk about the Fourier transform as changing functions in the time domain, changing functions in the frequency domain, and its inverse is going backwards, and that's true, but the Fourier transform itself operates on the space of functions. So it's an operator on functions, and those functions change their behavior. I will talk a little bit more in terms of advanced perspectives on this, but this operation amounts to diagonalizing. So all of the terms are orthogonal. So if we have a problem that's really hard in the time domain, we can turn that into a really easy problem in the frequency domain. And so this is the main application for people that solve really hard differential equations, right? They move things from the original domain into the frequency domain where everything is nice and orthogonal. They solve for all the coefficients, and they have solutions to hard differential equations. Again, this isn't rendering perfectly, but these are just the definitions of the Fourier transform. So this is the Fourier transform, this is the inverse operation. The Fourier transform takes a function in time domain, turns it into a function in the frequency domain, and the inverse Fourier transform takes a function in the frequency domain, turns it into the time domain. And these should be symmetric operations where you can go back and forth between them. One hard thing here is I've chosen one Fourier convention where these expressions look nice. There's almost always a factor that's floating out here. Everybody uses a different factor. Nobody communicates what their convention is. And so, good luck. Yeah, that really is the advice. That was the advice my advisor gave me. It's just, he'll figure it out. So, yeah. If you have questions about different Fourier conventions, feel free to reach out. It really helps to have somebody who's seen them all. But it can often be difficult to figure out what that factor is out there. Okay, so there's something else that shows up in astronomy a lot called the power spectrum. So I'll come back to that in a second, but some Fourier transform properties. So if f is a real valued and even function, then its Fourier transform is real and even. If f is a real valued and odd function, then its transform is odd and purely imaginary. And there's a bunch of these kinds of symmetries that you can use to make things easy. I hinted at this before. I may be given this as a condition at some point already, basically, for when this thing exists. But the Fourier transform is a linear operation. So if I take the Fourier transform of the sum of two functions, that's just the sum of the Fourier transforms. And I can also pull multiplicative constants up, right? And I suppose that that's at least, maybe it's harder to prove, but it's at least somewhat obvious, because if you had just a constant in front of these integrals, you can pull that out of the integral. So that should be at least something you can. There's something called the shift theorem. So if I shift in time, that results in a phase shift in the Fourier transform. And there's also a stretch theorem or a similarity theorem, which says that if I multiply in the time domain, I get these extra factors of 1 over whatever I multiplied in the frequency domain. Right? So, and that's because the time domain and frequency domain are kind of inverses of each other. So multiplication of one has to be 1 over the other. I tried to figure out like intuitive reasons why this has to be so. You actually make like the proof. It's just performing the Fourier transform in general. And yeah, I'll mention that we're going to come back to this a little bit in a problem that will cover the power spectrum, density. Okay, so really, so this slide introduces the power spectrum. The power spectrum is defined as the integral of the square of the function. Sorry, should be basically this one, right? The square of the Fourier transform integrated over all frequencies. That's called the power spectrum. An important result is called Parsifal's theorem, which says the energy in any representation of the signal is conserved, right? So if I have energy in a certain time window on this side, that has to give me the same energy in the corresponding region of frequency space, right? I can't have energy leaking into my signal from nowhere just by performing some linear operations on the signal. So the last thing, the notation here gets a little bit much. So this comes from the Cosmic Structures book that I mentioned, but I think this is interesting. It's an application in cosmology, so this is window functions and also generalizing the Fourier transform to higher dimensions. So if you want to generalize our operation from more than one dimension, we can just say we're replacing time with some potentially 3D coordinate. And then our frequencies also become a 3-vector. And then we have this the other new definition for the Fourier transform. So I have an integral over some volume, and I have some volume elements of d dimensions. Everything becomes a vector, and then everything that we just saw goes through exactly. So one application to this, as I mentioned, is studying 3D distribution of matter. So we can write that density contrast rho of R in terms of the B density, B cosmic density, whatever, it's conventional. Then the Fourier transform of the density contrast field is given by this expression. And then the power spectrum up to, as I mentioned, there's often conventional factors of something like 1 over the volume. So you get factor 1 over B here, but the power spectrum is just the expectation value of the Fourier transform of the density field in 3 dimensions. And this thing is an ensemble average we're making the approximation that since we don't actually have an infinite volume, that an average over the ensemble is the same as, yeah.
Just clarifying question. A couple of slides back, you introduced the power structure.
Yeah.
Was an integral over K.
What was that?
You said this is the power spectrum?
Yeah.
Like, it's integrated over K.
Yeah.
And then it's independent of K. But now in this slide, and generally in physics, power spectrum is a function.
Yeah. So I'll ask you to play around with this, but in practice, you're averaging over K windows to compute this thing. So you never have, there's a true power spectrum, which is going to be the whole integral, the whole power in the signal at all frequencies, right? The total power, this object is the power spectrum. The integral is the total energy. So in reality, in both cases, you average over the window, and then if you want to keep this thing for the cosmic density field, you're summing over tomographic bits or something. Right? Yeah.
Is K the wave number or the frequency? Or are you just changing the definitions?
So this is frequency here. Yeah. But you have,
but in the next slide, it's wave number because K dot R.
yeah.
Okay.
Yeah. So this is one of these things where you need to be careful with the notation. So I actually changed all these expressions to K from S at one point. These things can mean slightly different things. Check in the reference that you're working from what exactly. And I'll add a note on these slides about that. Okay. So yeah, so intuitively, the power spectrum is telling you the net contribution of some mode K to the stochastic process, which is the time series, regardless of what the underlying nature of that is. So the mode could be a 3D wave vector, or it could be 1D frequency or time series. So confusingly, right, the power spectrum, if I think of that as being key of some frequency, its Fourier transform is the correlation function in real space, right? And so this is another case where what we call, like, what the fundamental object is, what is the Fourier transform, and what is its inverse, is something that is field specific, and you kind of need to pick up based on the application that you're working with, which one you think of as the kind of fundamental object. And in principle, you should be able to obtain equivalent results, regardless of whether you work with the correlation function or the power spectrum. But often it's much harder to work with, say, a correlation function or a time series correlation or the time series signal itself compared to its Fourier transform. You're often also going to run into factors of something like in cosmology. There's often going to be floating factors of like the mean density or the mean density squared. So also be on the lookout for not only a normalization having to do with the Fourier convention, but also whether it's field-specific normalization, something like a factor of 1 over density. These are all things I got wrong, so I'm trying to make sure you don't make my mistakes. So yeah, as I mentioned, a cool application, or I should say, one thing we can do is we can also multiply these things by a window function. So if I have some window function in some region to localize my signal, then in Fourier space, I have to Fourier transform my window function, multiply it by the power spectrum. And in this case, it'll give me something like the mass variance on some scale. So the application here again is, turns out that the variance on some mass scale is tightly related to whether the process has a strong fractal dependence. So in cosmology, people have used these measurements of the mass variance to determine kind of the underlying physics of structure formation. Of course, also in cosmology, there's this parameter sigma 8, where you are taking the power spectrum of the window that is 8 megaparsecs in real space. So that's where sigma 8 comes from. Okay, realized that was a lot. I really wanted to stress to you, I wanted to give you a good resource for all this, but I also really wanted to stress to you the extent to which, in practice, things rely on conventions. You have to be really careful about all of the normalizations. And there's a lot of things that can go wrong in creating these representations. And so hopefully you've kind of seen that this is complicated and at least gotten a brief overview of it. In the problem set, you'll go through you'll get some practice with this, and I think a lot of things will be clearer. So I'm going to give you 4 problems. So one is compute the Fourier series for a discontinuous function. So that's going to be the triangle wave that I showed. You'll work with Fourier transform for periodic and aperiodic signals. So that'll be like sines and cosines, and also like the rect function. And the triangle wave and the rect function, two kind of classic examples that all like electrical engineering people have done many times. And then you'll recreate my Fourier transform as a limiting bounding function figure and see how that works. And that was super helpful for me getting into it. So I think that's a nice problem to work through. And then if you get through all that, there's a application of real Kepler light curve data. And as Adam said, that data has missing regions. So it has heteroscedastic errors that go to infinity, right? And so I'll ask you to do two things to try and fill in that missing data. So yeah, so that's the problem set. Can somebody check the schedule and tell me how close we are?
You have
5 minutes. Okay. So are there questions about any of this, or do we want to take the break 5 minutes early? Yeah.
Sorry, this is a major read, but I was a little bit confused when you were talking about justification for your series. You were talking about how, like, complex exponential gives you orthogonal basis. Can you explain that a little more?
Yeah. So this is something that you should like maybe write out also, right? Let me go back to that. I think the only thing on my slide was just the words that that's a true statement, right? But basically, so basically, right, if I want to figure out what the projection is, like how much of this term is how much of this term is represented by this particular complex exponential. What I'm going to do is I'm going to take dot products of the exponentials, right? Because that's going to give me something like the square root, something like the energy, or like it's a positive definite quantity. It represents the amount of this signal in this term, right? And so the fact that these are orthogonal means that all of the other terms are going to cancel when I do the integral, right? When I compute the dot product of this thing, I'm only going to get one term back, so I'm only going to get the contribution in that one complex exponential, right? Or that one set of cosine plus I sine, sine plus sine cosine, whatever Euler's identity is.
So something that I've heard in optical astronomy classes was the concept of fast Fourier transforms, FFTs.
Yeah.
So I've never really asked anybody what an FFT
is.
Yes.
Yeah. So let me see. I think I hid the slide, but I was originally going to have you write an FFT in today's problems.
Oh,
so
sounds.
I think it's not in here actually, but I will put it in the slides. So we're going to cover actually having you write out the FFT algorithm and do it exactly at the next session. So yeah, okay. So one problem with doing Fourier transforms is that it's a continuous operation on functions. So it can't be easily done on a computer, right? So to do it on a computer, you have to just come up with a discrete operation that looks like the Fourier transform. And you get these sums. It's like an infinite sum that you have to carry out, and on a computer you carry it out to some big number of terms to get whatever your position is, right? The fast Fourier transform uses some of the symmetries that I mentioned to break that sum up, but it does it in a recursive way. So the sum gets split into two terms, and then it gets split into two terms, and that recursion ends up, I think, it more than halves the number of terms you actually have to compute because you're using the intrinsic symmetries. But a lot of the weird behavior when you compute, like when you use NumPy's FFT that you're going to see in the problem section, a lot of the weird things where you're getting like a copy of the signal, basically you get two sets of terms. It's because it's a fast Fourier transform algorithm, and that other set of terms has to be with those symmetries. And again, I'm hopefully going to have you actually walk you through implementing that so you can see exactly where it comes from. But it's a software engineering thing, not a astronomy thing.
So I thought that the FFT happened at the position of where the data was collected. So like at the CCD itself.
So
that's where the FFT happened, and then the process data would come to you.
So
I'm not really sure about how.
Yeah. So I mean, so it's not happening physically, right?
Okay.
the radio telescopes measure like the Fourier transform of the sky for physical reasons, right?
Correct.
If something like FFTs were being performed in the electronics of the CCD, that is a thing that can definitely happen because this is a simple operation that is easily
Oh yeah,
easily
it's just
dynamic.
signal
Yeah,
processing.
yeah,
Essentially. Okay. Okay. Thank you.
All right, good questions. Any other questions? You guys look completely shocked.
The 1 minute, 7:45 now.
Okay.
Possible.
All right, so we'll be back in a half hour at 11:15, and we'll go into the problem set. So I'll have the problem set posted in the GitHub. You should also, at some point during the break, first things first, DSFP rule, you have to spend at least some portion of the break not looking at a screen. The portion of the break that you do spend looking at the screen, you should fork the repo and clone it to your machine. You should wait until after I put the problem set and these slides there. Have a good break.